moon in this decade and do the other things, not because they are easy, but because they are hard.
It's one small step for man, one giant leap for mankind. Absolutely, absolutely is a strong place here. I'll tell you, this road is really tough. You ready? I'll watch it real quick. Look at that.
In about 10 years, human beings will return to the moon. Here's what NASA thinks it will look like. The Crew Exploration Vehicle blasts off from the Kennedy Space Center. This four-person craft is headed for Earth orbit, where it will travel at 5 miles per second. A heavy-lift launch vehicle delivers the lunar landing vehicle, plus a powerful upper stage, to orbit. After docking between the Crew Exploration Vehicle and the lunar lander, the upper stage ignites and accelerates the whole stack to Earth escape velocity of 7 miles per second for translunar injection. The Crew Exploration Vehicle and lunar lander slow down to enter low orbit around the moon. On this mission, 4 men and women spend a week on the lunar surface. To get people into space, the Crew Exploration Vehicle is launched by a ship that uses a Space Shuttle solid rocket booster as its first stage. A new second stage helps the vehicle attain Earth orbit velocity of 5 miles per second. This picture compares the Crew launch vehicle with today's Space Shuttle. The shuttle system will have retired by the time flights to the moon begin, but the shuttle's engineering will live on in many of the moon vehicle's systems. The heavy cargo launch vehicle is built using shuttle external tank technology and the big shuttle main engines, which are among the most advanced rocket engines ever built. This new cargo vehicle can send more payload to translunar injection than the mighty Saturn V rockets of the 1960s. The Earth departure stage also is based in part on the shuttle external tank and provides the boost to Earth escape velocity, making the astronauts among the fastest human beings in history. The lunar lander looks like a much larger version of the Apollo-era lunar module. Not only can it land 21 tons on the moon's surface, this one has an airlock and a bathroom. This NASA slide shows where our 6 teams of astronauts landed during Apollo, in addition to the U.S. and Soviet robot probes. The yellow crosses show some of the highest priority sites for future landings. The Earth's axis of rotation is tilted 23½ degrees. In summer, our days are long because the northern hemisphere is tilted towards the sun. Because the moon's axis of rotation is only inclined 1½ degrees, there are no polar summers, no midnight sun on the moon. In fact, there are places on the moon where the sun never shines. That's exciting because it now appears that water from comet and asteroid impacts may be frozen in these cold places. The hydrogen and oxygen would be easy to extract and can serve as propellant and life support for the first lunar explorers. So don't be surprised if the first lunar base is located near the moon's south pole. Before our men and women set up a base on the moon, new generations of robotic explorers, prospectors, and robot builders will prepare the way. Experiments such as these at the Space Studies Institute at Princeton and the International Space University have proved that people can easily adapt to the 2.7-second round-trip time delay between the Earth and the Moon. Let's experience that 2.7-second delay ourselves right now. We learned the answers to some of the Moon's deepest mysteries thanks to the Apollo program. Before Apollo, no one knew if we could get to the Moon or live and work there. There was a big debate about whether lunar craters were caused by volcanism or by the impacts of asteroids and comets. And the biggest mystery of all, how was the Moon formed in the first place? Apollo demonstrated that we could get to the moon. 12 men spent a total of about 2 weeks on its surface, proving that we could live and work there. Our lunar explorations and analysis of the lunar samples has shown that nearly all of the moon's craters were caused by impacts. This was hugely important to all of us because scientists realized that the Earth was also bombarded by the same materials, even more than the moon. It is now believed that more than half of the water on Earth came from comets and asteroid impacts. That includes the water that makes up most of our body weight. The lunar samples also provided critical clues to solving the greatest lunar mystery of all, how the moon was formed. For centuries, scientists have proposed theories to account for our unique twin planet system. The 4 finalists in our lunar idol theory competition were: the co-accretion theory suggested that Earth and the moon were formed at the same time from the materials that made up the early solar system. The fission theory suggested that at one time the Earth spun so rapidly that a blob of material pulled free and became the moon. Charles Darwin liked this theory, but with the advent of modern computers it became clear that there is not enough residual angular momentum today to account for such rapid spinning eons ago. The capture theory suggests that the moon wandered into the neighborhood of the Earth and was caught by our gravity field. The giant impact theory suggests that about 4.5 billion years ago, a Mars-sized object slammed into the Earth, knocking debris into a ring around our planet that coalesced into the moon we know today. Astronomers have named this lost planet Theia, the mythological mother of Selene, the moon goddess in Greek mythology. And the winner is giant impact. Over the last 15 years, almost all scientists have converged on the giant impact theory. This painting by William Hartmann on the cover of Dana Mackenzie's excellent book, The Big Splat, illustrates what the impact between Theia and our ancient Earth might have looked like. The implications of the giant impact theory are profound. If the lost planet Theia had not collided with the Earth, life as we know it might never have originated. It also means that when the Apollo astronauts brought their 1,000 pounds of moon rocks back to the Earth, it reunited us with a part of ancient Earth. When we can use lunar materials to build solar power satellites, it will not only mean clean energy for the Earth. We can also use that energy to power fast travel in our solar system and beyond. Dr. Robert Forward, senior scientist of Hughes Aircraft, realized that the radio beam from a solar power satellite could accelerate a light sail to 5% of the speed of light in a week. He suggested that we test such satellites by using this 1-week boost to send robot missions to the nearest stars. This means that the generation that builds solar power satellites could see the first close-up views of the nearest solar systems in about 25 years. The moon, with its low gravity, abundant energy and material resources, and close proximity to the Earth, is the gateway to space. When humans first walked on the moon, they truly set us on a path to the stars. Dr. Kraft Ericke, one of the original spaceflight pioneers, said, "If God had wanted humans to fly in space, he would have given us a moon." Earth's offshore island is the stepping stone we need to explore the universe.